What lies at the heart of our galaxy? In the quiet vastness of the Milky Way, where rivers of starlight wind across the night, there is a silence that hides something immense. It has no glow of its own, yet its presence bends the path of light itself. It does not roar, yet it consumes. It does not move, yet the gravity it weaves holds entire star systems in its grasp. For centuries, astronomers gazed toward the galactic center and saw only mystery. Clouds of dust concealed the view, as though the cosmos were deliberately veiling its secret. Was it nothing more than a crowded cluster of stars? Or something darker, more profound? Each new observation brought the unsettling truth into sharper focus. Buried in that hidden core is a singular presence, Sagittarius A. A black hole 4 million times the mass of the Sun, compressed into a space no wider than Mercury's orbit. It is invisible, silent, patient, yet its influence is undeniable. Stars whip around it at breakneck speeds, their paths contorted into elegant, impossible arcs. Time itself stretches near its edge, as though the universe were slowing to a whisper. To look into this darkness is to confront a paradox. Here lies the greatest concentration of mass we know, wrapped in silence, a place where the laws of physics falter, and where human knowledge reaches its breaking point. What happens beyond that horizon? What becomes of matter, of energy, of time itself? This is the story of the galaxy's beating heart. A story of discovery, terror, and wonder. For to unravel the mystery of Sagittarius A is to question not only the universe, but the very limits of existence. At the dawn of modern astronomy, the center of the Milky Way remained a place of shadows. The naked eye could see only a faint swelling in the constellations of Sagittarius and Scorpius, a pale haze set against the sweep of the galactic bulge. Early astronomers suspected it was a gathering of countless stars, a dense cluster glowing through the veil of interstellar dust. Yet beneath that veil something waited. In the early 20th century, astronomy began to change. The telescope had already transformed humanity's view of the heavens, but a new way of listening was about to emerge. Radio astronomy. No longer bound by visible light, scientists could now capture signals that pierced the dusty shroud around the galactic center. What appeared opaque to human eyes became transparent to long, invisible waves. The galaxy, once silent, began to hum. By the 1950s, radio telescopes detected unusually strong emissions streaming from the direction of Sagittarius. The signals were intense, concentrated. Unlike the broad whisper of ordinary stars, it was as if some hidden engine pulsed with energy behind the curtain of dust. But no one could yet explain its nature. Then in 1974, two young astronomers, Bruce Ballack and Robert Brown, turned their instruments toward this mysterious source. Using the Green Bank Interferometer in West Virginia, they discovered something extraordinary on a compact, bright radio beacon at the heart of the Milky Way. They named it Sagittarius A, the asterisk denoting its peculiar star-like intensity. It was no sprawling cluster. It was pinpointed, concentrated, impossibly small in angular size, yet dazzlingly powerful. Skepticism followed. Some argued it might simply be a dense cluster of massive stars, their energies combining into a radio glow. Others suspected it could be a unique stellar remnant, perhaps a neutron star on a scale never before observed. But the evidence defied these explanations. To pack such enormous energy into such a confined space required densities beyond imagination. Slowly, a radical idea emerged. Perhaps the only object capable of producing such compact power was something never before confirmed on this scale: a supermassive black hole. It was an unsettling proposition. Black holes were still largely theoretical, the exotic byproducts of Einstein's equations. A single collapsed star perhaps could be a black hole, but an object millions of times the mass of the Sun residing in the quiet heart of the Milky Way, that was almost unthinkable. Yet the galaxy itself seemed to demand this explanation. The trouble was, the center of the Milky Way remained shrouded in obscurity. Clouds of interstellar dust swallowed visible light, erasing the view from optical telescopes. If a black hole lurked there, it could not be seen in any ordinary sense. Astronomers needed new eyes, instruments capable of piercing the smoke and haze of the galactic core. Infrared light offered a path forward. Unlike visible light, infrared waves could slip through the dusty shroud, carrying with them a faint but vital record of what lay within. By the late 20th century, infrared astronomy began to open that hidden window. The development of adaptive optics sharpened the view even further, correcting the blurring effects of Earth's atmosphere. For the first time, astronomers could peer into the galactic center with clarity. What they saw defied expectation. Stars near Sagittarius A were not drifting lazily as in other parts of the galaxy. They were racing. Bright giants visible only in the infrared, whipped through space at thousands of kilometers per second, following paths twisted into near-perfect ellipses. These were not random motions. They traced invisible orbits around a common point. But at that central point there was nothing. No visible star, no shining cluster, only darkness. One star in particular, known as S2, became a cosmic test subject. Every 16 years it swoops perilously close to the unseen object, traveling at speeds exceeding 7,600 kilometers per second. Its orbit, mapped meticulously over decades, revealed the truth with astonishing precision. Only a single entity could account for such extreme gravity. Within a region smaller than our solar system's inner planets, 4 million solar masses were packed into invisibility. It was, beyond doubt, a supermassive black hole. For astronomers, the discovery was both exhilarating and terrifying. The Milky Way, our cosmic home, was not a tranquil island of stars drifting through the void. It was bound together by a monster. Its heart was not a brilliant beacon of creation, but an abyss from which no light could escape. Yet even in silence, Sagittarius A spoke. The flicker of X-rays revealed flares of energy, perhaps from gas and dust falling into its maw. Radio waves pulsed with strange rhythms, whispers of matter spiraling toward the edge of forever. Every signal carried the same haunting truth. The center of our galaxy is governed by a force that lies beyond the known laws of physics. The rise of new instruments, the Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Chandra X-ray Observatory in orbit, brought its features into sharper relief. They showed not only the furious orbits of nearby stars, but also the occasional outburst, brief eruptions of energy as matter brushed against the event horizon and was torn apart. The black hole itself remained invisible, yet its shadow grew undeniable. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez, who had spent decades tracking those stellar orbits. Their meticulous work proved what had long been suspected. At the center of the Milky Way, concealed behind dust and silence, lies a supermassive black hole. And still the questions deepened. How did it form? Did it grow from the collapse of a single massive star in the galaxy's youth? Or did it swell by consuming others, merging with black holes born in ancient collisions? Why does nearly every galaxy from dwarfs to giants seem to harbor such a dark heart? These mysteries remain unsolved. Each answer brings new uncertainties, each revelation a reminder of how little is known. Yet one truth is certain. The discovery of Sagittarius A reshaped humanity's understanding of its own galaxy. What once seemed like a serene gathering of stars was revealed as a dynamic system. Its fate bound to the gravity of an invisible titan. The story of its discovery is not just a tale of technology or scientific progress. It is a story of perspective, of learning to see what cannot be seen, to listen where silence seems complete. It is a story of patience as decades of observation carved a picture from the faint motions of distant stars, and it is a story of humility, for in peering into the galactic center, humanity confronts forces that dwarf imagination. Every orbit, every flare, every radio pulse reminds us of the same truth. The galaxy we call home is shaped by an unseen abyss. It does not shine, yet it defines the architecture of the stars. It does not speak, yet it governs the rhythm of time and motion. In this realization, awe and unease intertwine. For at the heart of the Milky Way, the boundary between knowledge and mystery is not a line. It is an event horizon. The night sky has always seemed eternal, its stars appearing steady and unmoving to the human eye. But deep in the hidden center of the Milky Way, the stars tell a different story. They are not fixed beacons. They race, they bend, they whirl in patterns dictated by a force unseen. Their motion carries with it one of the most profound scientific revelations of our time. Among them, one star became a messenger. Designated S2, it is small compared to the giants of the galaxy, yet its orbit holds the weight of cosmic truth. Every 16 years it sweeps around the galactic center, slingshotting past an invisible point at speeds so extreme, they defy ordinary comprehension. At its closest approach, S2 hurtles through space at more than 7,600 kilometers per second. In a single heartbeat, it covers the distance from London to New York. Its trajectory is no wandering path. It is an elegant ellipse carved into space, its every curve pulled tight around a mass that cannot be seen. For decades, teams of astronomers tracked its dance. At the Keck Observatory atop Mauna Kea in Hawaii, and at the Very Large Telescope high in the Chilean desert, instruments refined by adaptive optics captured the faint glimmers of S2 and its companions. Year after year, patient observation mapped their arcs with precision. What emerged was no ordinary gravitational story. The data revealed that these stars were not orbiting a cluster of other stars, nor some vast but diffuse cloud of dark matter. Such structures would blur, dissolve, or scatter under the ferocity of their own density. Instead, the orbits pointed to a single, compact source of gravity, one so concentrated that 4 million suns were crushed into a region no larger than the orbit of Mercury. Nothing else in the known universe could achieve such compression. Nothing except a supermassive black hole. For the scientific community, this realization struck like a thunderclap. Black holes had long been predicted by Einstein's general theory of relativity. They were mathematical consequences of the way gravity bends space and time. But for much of the 20th century, they hovered at the edge of belief. Exotic possibilities, perhaps too strange to be real. Even stellar mass black holes born from the collapse of individual stars were elusive and indirect in their evidence. To suggest that 1 million of times larger sat at the center of our galaxy was almost beyond imagination. And yet the evidence was undeniable. The precise tracking of S2 and neighboring stars showed orbital patterns that fit one explanation, and one explanation only: a point-like mass of extraordinary density. This was no wandering theory. This was direct observable proof. The heart of the Milky Way was a black hole. The implications reverberated through science. What had once been thought of as rare theoretical curiosities were revealed to be central to galactic life. The black hole at Sagittarius A was not merely present, it was essential. It anchored the orbits of millions of stars, holding the galaxy's spiral arms in their sweeping arcs. The Milky Way itself, it seemed, was defined by the gravity of this hidden abyss, and with that revelation came awe and unease. A black hole 4 million times the mass of the Sun is a concept almost beyond comprehension. To compress such weight into such confinement is to push physics to its breaking point. The event horizon, the invisible boundary beyond which nothing escapes, spans only about 25 million kilometers. In cosmic terms, it is smaller than the space encompassed by the orbit of Mercury, a galactic heart squeezed into silence. The shock was not just in the numbers. It was in the confirmation that Einstein's strange, abstract equations described reality at a galactic scale. The curvature of space-time, once a poetic idea scribbled in mathematics, was now visible in the paths of stars. The bending of light, the stretching of time, the warping of orbits, all of it played out in the skies above, as though the universe itself were demonstrating the laws of relativity. Skepticism gave way to acceptance, and acceptance to wonder. The discovery of S2's orbit and the invisible object that commanded it earned Reinhard Genzel and Andrea Ghez the Yale Nobel Prize in Physics in 2020. Their decades of work had drawn the first clear map of a supermassive black hole, transforming speculation into certainty. But certainty brought with it new questions. If such a colossal black hole could hide in the center of our own galaxy, then how many others waited across the cosmos? Observation soon revealed that almost every galaxy, from the smallest dwarfs to the largest ellipticals, carried its own dark heart. Black holes, once thought to be anomalies, were revealed as architects of structure, shaping the growth and destiny of galaxies themselves. The scale of the revelation was dizzying. The universe, it seemed, was built not only on light but on shadow. Creation itself was partnered with destruction, and at the core of every great island of stars lay the same abyss. For humanity, the discovery was more than a scientific achievement. It was a confrontation with limits. To understand S2's orbit is to grasp that within that tiny invisible point lies a collapse so complete that matter, energy, and even time itself are drawn into silence. The laws of physics as we know them cease to function beyond its horizon. Equations fail. Prediction falters. The black hole is not only an object, it is a boundary of knowledge, And yet it is also a reminder that in the quiet motions of distant stars, secrets of unimaginable magnitude are written, that patient observation, measured year by year, can pull truth from the void, and that at the heart of the Milky Way, the universe itself whispers of mysteries still beyond reach. The scientific shock of Sagittarius A was not the end of a story. It was the beginning. For with its discovery came the realization that black holes are not distant curiosities, but central players in cosmic history. They govern galaxies, sculpt light, and challenge the very foundations of understanding. The stars orbiting that darkness, racing at impossible speeds, are not merely celestial bodies. They are heralds of a truth that shakes the balance between what is known and what is unknowable. They show us that Einstein's equations drawn a century ago were not only mathematics but prophecy, predictions written into the very structure of the cosmos. And so the galaxy is revealed as a place where the familiar gives way to the extraordinary, where the serene glow of starlight masks a hidden engine of unimaginable gravity, where the universe itself bends to the will of the unseen. At the center of it all, S2 continues its dance. Patiently, silently, it traces its ellipse, marking the passage of years, measuring the gravity of an abyss. Each orbit is another reminder, another confirmation, another invitation to peer deeper into the heart of darkness. The shock has passed, but the wonder remains. For in the galactic core, where light itself is bound and time is stretched thin, the universe reveals its most humbling truth, that even in silence, gravity speaks. At the center of the Milky Way, the stars continue their silent ballet, circling an invisible heart. Their orbits, measured year after year, became more than curiosities of motion. They became a ledger of proof, a record written in gravity itself. No single observation would have been enough. But decades of patience, persistence, and technology slowly peeled back the veil, revealing the truth of Sagittarius A. In the late 20th century, two rival teams emerged, separated by continents but united in pursuit of the same enigma. In Germany, Reinhard Genzel and his colleagues built an ambitious program at the European Southern Observatory, wielding the power of the Very Large Telescope, high in Chile's Atacama Desert. Across the ocean in California, Andrea Ghez and her team at UCLA pushed the Keck Observatory in Hawaii to its limits. Each team refined the art of adaptive optics, bending the turbulence of Earth's atmosphere into submission, sharpening the faint glimmers of stars near the galactic core into resolvable points of light. What followed was a triumph of patience. Year after year, each team traced the positions of those stars, measuring their shifts against the backdrop of the heavens. The orbits tightened into clarity. One by one, they fell into patterns around an invisible focus. And then there was S2, the star whose 16-year circuit passed perilously close to the abyss. As its arc was mapped in exquisite detail, the conclusion became unshakable. Only a supermassive black hole could govern such motion. The magnitude of the revelation did not pass quietly. In 2020, the Nobel Prize in Physics was awarded to Genzel and Ghez for proving the existence of Sagittarius A, a recognition not just of discovery, but of endurance. Their work spanned decades, requiring instruments that had not existed when they began, and perseverance against skepticism that lingered long into their careers. The galaxy's dark heart was no longer speculation, it was fact. And yet, even in confirmation, Sagittarius A revealed new mysteries. It is not a silent void, not entirely. Occasionally, faint flickers of X-rays flare from its edge. Chandra, NASA's orbiting X-ray observatory, recorded bursts of high-energy radiation from the galactic center, signals of matter in its final moments before destruction. Clouds of gas spiral inward, their atoms stretched and torn, heated to millions of degrees by friction as they are whipped around the event horizon. For hours, the black hole glows faintly in the invisible light of X-rays, before the flare collapses into silence once again. These brief outbursts are whispers of a feeding process that is, for Sagittarius A, strangely subdued. Unlike the blazing quasars seen in distant galaxies, devouring entire stars and radiating with the brilliance of trillions of suns, our galaxy's black hole is quiet. It consumes sparingly, as though the gas and dust at its doorstep are reluctant to fall in. Still, when a dense clump strays too near, shock fronts ripple through the surrounding medium, heating clouds of hydrogen and creating momentary flashes of activity. Each flare is a glimpse into a process we can never fully see, matter crossing the threshold of no return. The scale of the event horizon itself is a sobering reflection of the black hole's density. For Sagittarius A, its edge lies a mere 25 million kilometers from its center. That is less than the orbit of Mercury. Yet within that tiny sphere lies the mass of 4 million suns. The numbers strain human imagination. Imagine compressing the Earth until it was no larger than a marble. Imagine compressing the sun until it was the size of a city. Sagittarius A takes such compression to an extreme beyond reason, crushing stars' worth of matter into a silence from which not even light escapes. Around this abyss, the surrounding environment bears the scars of its gravity. Clouds of gas are shredded into filaments, their atoms heated and ionized by tidal forces. Radio telescopes detect structures that resemble shock waves, ripples created as streams of matter collide at near relativistic speeds. These clouds, like comets around a hidden star, drift too close and are torn apart. What survives is twisted into luminous arcs, briefly illuminating the otherwise invisible heart. But if the black hole itself cannot be seen, could its shadow ever be captured? This question led to one of the most audacious efforts in modern astronomy, the attempt to image the unseeable. No single telescope could achieve the resolution needed to observe the event horizon's silhouette. Instead, astronomers turned to interferometry on a global scale. By linking radio observatories across continents, they created an Earth-sized virtual telescope, the Event Horizon Telescope. This network of instruments, synchronized across the globe, gathered signals with extraordinary precision. Each telescope captured fragments of Sagittarius A's radio emissions, which were then combined through vast computational effort. The result, after years of coordination, was humanity's first glimpse of the shadow of a black hole. In 2019, the Event Horizon Telescope unveiled its historic image of M87's black hole, a glowing ring of light bent by gravity into a fiery halo around darkness. 3 years later, in 2022, the same collaboration revealed the shadow of Sagittarius A. Though more difficult to capture, blurred by the turbulence of matter and magnetic fields, it bore the same unmistakable form, a glowing circle encasing a void. The image was not merely a photograph, it was a confirmation of Einstein's predictions, sketched now not in mathematics but in light. The scientific triumph carried with it a deeper resonance. For the first time, humanity had looked directly at the abyss that lay at the center of its own galaxy. The shadow was more than a picture, it was a symbol. Proof that even the darkest places in the cosmos leave their mark. Proof that even silence can be seen. And yet every answer deepened the questions. Why is Sagittarius A so faint compared to other supermassive black holes? Does it starve in the emptiness between stars? Or does its gravity fling matter away before it can be swallowed? How do its flares originate? And what do they reveal about the magnetic fields that twist around its edge? These puzzles remain unsolved, dangling at the boundary between observation and theory. The deeper the investigation went, the more profound the philosophical weight became. Here was an object that both defined and defied the universe. Its presence shaped the Milky Way itself, yet its nature undermined the very physics designed to describe it. Einstein's relativity still held astonishingly in the arcs of stars and the bending of light. But what lay beyond the horizon, the realm where density becomes infinite, where equations collapse into paradox, remains unknowable. Sagittarius A is thus not only a scientific object, but a boundary of understanding. Every orbit tracked, every flare detected, every pixel of its shadow imaged, brings us closer to the edge of knowledge itself. Beyond that edge lies mystery, and in that mystery is both fear and wonder, the fear of what cannot be known, and the wonder that such questions can even be asked. The long-term monitoring of its stars, the detection of its flares, the mapping of its shadow, these are not just technical achievements. They are acts of persistence against the void. They are proof that human curiosity can reach into the deepest darkness and return with light. Sagittarius A is no longer a rumor hidden behind dust. It is a confirmed presence, a cosmic truth at the heart of our galaxy. But confirmation has not diminished its strangeness. If anything, it has deepened it. For the more we learn, the more we are reminded that the universe is built not only of what can be known, but also of what may forever remain beyond reach. And so the investigation continues. Each night, telescopes turn their gaze toward the center of the Milky Way. Each signal, each orbit, each flare is another piece of a puzzle with no guarantee of completion. But in the pursuit itself lies meaning, for in studying Sagittarius A, humanity is not merely measuring the mechanics of a black hole. It is confronting the boundary between knowledge and mystery, between light and shadow, between existence and its silence. For centuries, the center of the Milky Way was a place of speculation, a hidden core concealed by dust and silence. But in the 21st century, the silence was broken in a way no one could have predicted. Across the globe, scientists came together in a collaboration that spanned continents. Their goal was audacious: to capture the unseeable, to look directly at a black hole. It was called the Event Horizon Telescope, or EHT. Not one telescope, but many. Radio observatories scattered across Earth, from Hawaii to Spain, from Chile's deserts to the South Pole, were linked into a single network. Together they formed a planet-sized instrument, using a technique known as very long baseline interferometry. Each dish captured fragments of faint radio waves, and when synchronized with atomic clocks of extraordinary precision, the fragments combined to create a single image. The EHT was, in effect, the largest telescope ever built. Its first target was not Sagittarius A, but a black hole in a distant galaxy known as M87. 55 million light-years away, M87's supermassive black hole is colossal, 6.5 billion times the mass of the Sun. Its vast scale made it easier to image, for though it lay farther away, its shadow was larger, more stable, less prone to flicker. In 2019, the world held its breath as the image was unveiled, a glowing ring of light bent by gravity into a halo of fire, surrounding a perfect void. For the first time, humanity had looked directly at the abyss. But the true test was still to come. After M87, the eyes of the EHT turned inward, toward the heart of our own galaxy. Sagittarius A awaited. Here the challenge was far greater. Though 4 million times the mass of the Sun, Sagittarius A is tiny compared to M87's Leviathan. Its event horizon spans no more than 25 million kilometers, vast by human standards but minuscule on the scale of galaxies. To capture its image was like photographing a grain of sand on the moon from Earth. And unlike M87's steady beacon, Sagittarius A flickers. Matter swirls into it in unpredictable bursts, changing brightness on timescales of minutes. For the EHT, which gathers light over hours, the black hole shifted beneath their gaze, smearing the image into a blur. Years of analysis followed. Teams sifted through torrents of data, calibrating, refining, testing models against reality. Supercomputers reconstructed fragments into coherence, peeling away distortions to reveal the truth beneath. And then, in May of 2022, the first image of Sagittarius A was revealed. It was a moment unlike any other in science. For the first time, humanity stared into its own galactic heart. The shadow of the Milky Way's black hole emerged, a dark void encircled by a ring of glowing gas, distorted by gravity into a perfect cosmic silhouette. It was not as sharp as M87's fiery halo, but it was ours, the abyss around which every star of the Milky Way turns. The image confirmed Einstein's predictions once more. The size of the shadow matched the mass derived from stellar orbits. The ring glowed with the telltale signature of gas accelerated near light speed, its light bent into a halo by warped spacetime. The shadow of Sagittarius A was real, and it was exactly where the equations said it should be. And yet with confirmation came mystery. Despite its mass, Sagittarius A is faint. Compared to the blazing hearts of other galaxies, quasars, active galactic nuclei, our black hole is quiet. Those others devour matter with insatiable hunger, spewing jets of plasma across intergalactic distances, glowing with the brilliance of trillions of stars. But Sagittarius A seems almost dormant, consuming only a trickle of gas and dust. It flares occasionally, releasing brief outbursts of X-rays, but for the most part it slumbers. Why is it so calm? Has it always been this way? Astronomers suspect not. Across cosmic history, galaxies have flared into brilliance as their central black holes gorged on matter. Some believe that billions of years ago, Sagittarius A might have burned as a quasar, a blazing lighthouse rivaling the brightness of the entire Milky Way. If so, it has since fallen silent, starved of fuel, a predator without prey. But could it awaken again? Could the heart of our galaxy flare once more, transforming the night sky with its fury? The evidence suggests it is possible. Occasionally, a gas cloud drifts perilously close to the abyss, distorted into luminous arcs before disappearing. Some theories suggest that entire stars may wander too near. When they do, the results are catastrophic. The tidal forces of the black hole stretch and tear the star apart in what is known as a tidal disruption event. For weeks or months, the remains blaze in radiation as they spiral inward, before being swallowed into silence. Such events have been seen in other galaxies, sudden flares of light marking the destruction of stars at the edges of black holes. For now, Sagittarius A has not revealed such a spectacle in modern observation, but the possibility lingers, a reminder that the calmness of today may not last forever. If a star were to be torn apart at the edge of our own galaxy's black hole, the consequences would be profound. The night sky would glow with radiation. Telescopes across the world would capture the last light of a dying sun, and humanity would witness its galactic heart awakening, however briefly, from its quiet slumber. For now, however, Sagittarius A remains subdued. Its faint flickers remind us of its presence, but it does not rage. Its shadow captured at last is a picture not of violence but of silence. And perhaps that is its strangest quality of all. For an object so massive, so central, so essential, it hides in humility, offering only whispers where others scream. The deeper the investigation goes, the more profound the questions become. Was our galaxy shaped during an age when Sagittarius A was brighter, more violent, more active? Does its silence today mean safety? Or does it conceal a potential for fury yet to come? And why, across the vastness of the cosmos, do black holes shift between such extremes, from roaring quasars to near invisibility? These are questions without answers, at least not yet. But in the shadow of Sagittarius A, the pursuit of answers has already changed humanity's relationship with the universe. The first image was more than science. It was philosophy rendered in light. It was a mirror, showing not only the black hole itself, but the persistence of a species that dared to look. The escalation of discovery is not just in technology or collaboration. It is in perspective. For every new revelation deepens the mystery, expanding the horizon of what we do not yet know. The black hole at the center of the Milky Way is no longer speculation. It is fact. Yet the meaning of that fact continues to unravel. In its silence, Sagittarius A reminds us of fragility. In its shadow, it reminds us of humility. And in its image, captured across continents, it reminds us that even in the face of darkness, humanity can create light. The mystery deepens. The heart of the galaxy beats quietly for now, but with a power that could awaken at any time. And as we continue to stare into its shadow, we confront not only the limits of knowledge but the limits of existence itself. Near the center of the Milky Way, gravity takes its final form. Around Sagittarius A, space-time itself bends into a geometry so extreme that it becomes a testbed for the greatest ideas in physics. It is here, in the silent grip of 4 million suns compressed into a shadow smaller than Mercury's orbit, that human theories meet their limits. Einstein's general relativity still holds sway. His equations predict with astonishing accuracy the orbits of stars like S2, the bending of light around the abyss, the size of the shadow seen by the Event Horizon Telescope. For a century, relativity has stood unbroken, its mathematics unfolding into the very structure of the cosmos. Yet even Einstein's brilliance falters at the horizon. Relativity describes gravity as geometry, a smooth fabric curving under mass. But at the center of a black hole, that smoothness collapses into a singularity, a point of infinite density, where time and space themselves are thought to end. Infinity, however, is a warning sign in physics, a signal that something is missing. General relativity cannot explain what happens inside. It is a map that ends at the edge. To move further requires another theory, one that merges gravity with quantum mechanics, the science of the very small. And here the mystery deepens into speculation. Quantum theory suggests that black holes cannot be truly silent. In the 1970s, Stephen Hawking proposed that pairs of virtual particles appear at the edge of the horizon. One falls in, the other escapes, creating a faint glow now called Hawking radiation. If true, black holes are not eternal. They evaporate, shrinking across unimaginable spans of time until they vanish entirely. For Sagittarius A, this evaporation would take longer than the current age of the universe by a factor so vast it defies comprehension. Yet the idea transformed black holes from eternal prisons into finite players in cosmic history. But what lies inside the horizon itself? Some physicists imagine that the singularity is not truly a point, but something hidden by the limits of our mathematics. Could it be a bridge? A wormhole leading to another region of the universe, or even to another universe entirely? Einstein himself once speculated about such Einstein-Rosen bridges. In theory, space-time could fold in on itself, creating shortcuts across the cosmos. But in practice, such wormholes may be unstable, collapsing before anything could pass through. Still, the idea lingers that Sagittarius A could be more than a destroyer. It could be a gateway. Others propose stranger possibilities. The firewall paradox suggests that the horizon may not be smooth, as relativity predicts, but searing. In this view, any particle or person crossing the edge would be instantly incinerated by a wall of energy. This clashes with relativity's principle that nothing unusual should happen at the horizon. The paradox remains unresolved, a riddle at the boundary of two great theories. These speculations highlight a deeper truth, that black holes are more than astronomical curiosities. They are laboratories of the extreme, where the laws of physics are stretched to breaking. Whatever theory eventually unites relativity and quantum mechanics will almost certainly pass through the shadow of a black hole. Sagittarius A is not just a test of physics, but of cosmic history. Supermassive black holes are found at the centers of nearly all galaxies. Their masses are not random. They scale with the size of the galaxies that surround them. This strange relationship hints that galaxies and black holes grow together, their fates intertwined. Did Sagittarius A help sculpt the Milky Way? Did its gravity shepherd the early gas clouds that collapsed into stars, shaping the spiral arms we see today? Evidence from other galaxies suggests that black holes may act as engines of formation. When active, their jets and radiation can blow gas outward, regulating star birth on galactic scales. They destroy and create in the same act, heating some regions while triggering collapse in others. Sagittarius A, though quiet now, may once have played this role in the early Milky Way, blazing as a quasar before retreating into silence. In its shadow lies not only destruction but creation. This duality, engine and destroyer, is what makes black holes so profound. They are devourers of matter, collapsing stars and swallowing light. Yet they are also anchors of galaxies, their gravity binding billions of stars into coherent structures. They are both predators and architects, both end and beginning. For philosophers of science, Sagittarius A becomes more than an object. It becomes a symbol, a reminder that the universe is built on paradox, that creation and annihilation are woven together, that knowledge and mystery grow from the same soil. To study the black hole at the heart of the Milky Way is to confront the limits of what can be known, and to accept that beyond those limits lies a darkness we may never cross. And yet even in speculation there is meaning. Each theory, wormholes, firewalls, Hawking radiation, singularities, is not just a guess at what lies beyond, but a reflection of human imagination pressed against the frontier. The black hole challenges us not because it is unknowable, but because it demands that we try to know. Perhaps in the far future, new generations will look at Sagittarius A not just as a shadow, but as a key. A key to unifying the great theories of physics, a key to understanding the origins of galaxies, perhaps even a key to other universes if the boldest speculations prove true. For now it remains a silence at the heart of the Milky Way, but within that silence possibility resides. Sagittarius A forces us to ask questions not only of the cosmos, but of ourselves. What does it mean to live in a galaxy whose heart is a void? What does it mean to measure time and existence against something that erases both? And what does it mean that even in destruction there may be creation, that even in silence there may be a song too faint for us yet to hear? The answers may never be complete, but the pursuit itself reveals the most human truth of all, that we are a species willing to stare into the abyss, not with fear alone but with wonder, and in the faint glow around Sagittarius A, in the orbits of stars drawn by its gravity, in the theories spun from its mystery, we glimpse not just the heart of the galaxy, but the heart of knowledge itself. The heart of the Milky Way is silent, but humanity has found ways to listen. No single eye can see it clearly. No single instrument can capture its complexity. Instead, an orchestra of machines spread across the earth and beyond works in unison to reveal what hides within the dark center. These tools are not merely instruments of observation, They are extensions of human curiosity, machines designed to stretch perception to the very edge of physics. The Event Horizon Telescope remains one of the boldest of these endeavors. Its strength is not in one place, but in many. Radio dishes scattered across the globe. From the deserts of Chile to the icy plateau of Antarctica, from the volcanic peaks of Hawaii to the dry plains of Spain, are joined together as though the Earth itself had become a single telescope. Through very long baseline interferometry, signals are captured with precision so fine that atomic clocks are required to synchronize them. Only when all the data is brought together can an image emerge, pixel by pixel. A map of light bent by gravity at the edge of the abyss. From this network came the first image of Sagittarius A, a picture that was less a portrait than a revelation. And yet the EHT is not finished. Future expansions will add more telescopes, increase sensitivity, and sharpen clarity. The dream is not only to capture still images, but to create movies, real-time films of matter spiraling into the event horizon, flickering as it vanishes into darkness. Such a vision would turn the theory of relativity into a living performance, written in light across the sky. But the Event Horizon Telescope is only one part of the effort. In Chile's Atacama Desert, where the air is thin and dry, the Very Large Telescope peers into the galactic center with a different kind of precision. At its core is an instrument named gravity. This device combines the light from multiple telescopes, stitching their vision into a coherent whole. With gravity, astronomers can track the motion of stars with accuracy measured in micro-arcseconds. The ability to discern a shift no larger than a coin seen on the surface of the moon. Through gravity, the star S2 became more than an orbiting body. Its path revealed the subtle fingerprints of Einstein's predictions. As it swept near the black hole, its light stretched into redshift, lengthened by gravity itself. Space and time warped, and the instrument caught it, a confirmation of relativity on a stage no laboratory could replicate. Now the same instrument continues its vigil, measuring every flicker of starlight, every deviation in orbit, every chance to glimpse phenomena that might hint at new physics beyond Einstein's map. Above Earth, the Chandra X-ray Observatory circles in silence. It does not see in visible light nor in radio, but in high-energy radiation. To Chandra, Sagittarius A is not a shadow but a pulse. Every so often, gas and dust spiral inward, heated to millions of degrees as they approach the point of no return. When this happens, Chandra detects sudden bursts of X-rays like faint sparks from a hidden forge. These flares last only hours, but each one tells the story of matter's final moments. By studying their brightness, timing, and frequency, astronomers hope to understand why our black hole flickers so quietly, and why it does not rage with the brilliance of its distant cousins. Even newer tools are arriving. The James Webb Space Telescope, floating beyond the obscuring atmosphere of Earth, has already turned its gaze toward the galactic center. Its infrared vision cuts through the dust that blinds ordinary telescopes, revealing structures and stars that once hid in darkness. With Webb's unprecedented sensitivity, astronomers hope to watch faint stars orbiting ever closer to the abyss, their light distorted by gravity into subtle signals of relativistic effects. And there are plans for more. Concepts for next-generation interferometers promise even sharper resolution. Future radio arrays could map the turbulent dance of plasma around the horizon with greater fidelity. Some designs even envision observatories stationed in space, free from the distortions of the atmosphere, linking together across orbital distances to create images of unmatched clarity. Each of these instruments seeks more than pictures. They seek the fine details that separate theory from truth. Among them is the search for frame dragging, the twisting of spacetime itself caused by the black hole's spin. If Sagittarius H rotates as most black holes are expected to, then its gravity does not merely pull. It drags spacetime around with it, like a whirlpool twisting the river that feeds it. Detecting this subtle effect would be another confirmation of relativity, and perhaps a step toward glimpsing the black hole's hidden interior. Gravitational redshift, too, is under constant scrutiny. As light struggles to escape the gravity well of Sagittarius A, it stretches into longer wavelengths, a cosmic echo of its ordeal. Instruments like gravity have already detected this effect in S2, but the quest continues to measure it more precisely, and in other stars that circle closer still. Every detection is another chisel mark against the stone of uncertainty, Another piece of evidence that space-time bends exactly as Einstein imagined. Or perhaps one day differently. Beyond these electromagnetic observations lies another frontier: gravitational waves. The ripples in space-time first detected in 2015 came from smaller black holes colliding in distant galaxies. But around Sagittarius A, there may be similar events on a different scale. Stellar mass black holes wandering close to the supermassive heart could merge or spiral inward, sending out faint tremors in the cosmic fabric. Detecting such signals near Sagittarius A could offer a new kind of observation, not of light but of space-time itself vibrating with the rhythms of collapse. Instruments like the future LISA mission, a gravitational wave observatory in space, may one day capture these whispers, adding a new voice to the symphony of the galaxy's heart. This ongoing effort is not merely technical. It is philosophical. Each tool is designed to probe the limits of knowledge itself. Together, they ask questions that are as ancient as they are modern. How does time behave near the edge of forever? Does matter truly vanish, or is something preserved in ways we cannot yet imagine? Is gravity, as Einstein described, the final word? Or is it only an approximation, hiding deeper truths beneath its elegance? In the marriage of theory and observation, science finds its balance. Theories stretch toward speculation, imagining singularities, wormholes, firewalls, and evaporation. Observations pull back, grounding thought in evidence, in orbits, in flares, in shadows, in whispers of radiation. Neither alone can unlock the mystery. Together they form the dialogue that defines human progress. Sagittarius A is not static. It is a dynamic system, changing in subtle ways over years, decades, centuries. The instruments that watch it are engaged in a long pursuit, one that may span lifetimes. What is invisible today may become clear tomorrow. What is only theory today may be evidence tomorrow. And so the work continues. Night after night, telescopes turn their gaze toward the galactic center. Data is gathered, compared, refined, tested against models of spacetime. Each flare captured, each orbit measured, each photon traced adds to a growing mosaic of truth. The mystery remains, but the shape of the unknown becomes clearer with every observation. The story of Sagittarius A is not just the story of a black hole. It is the story of humanity reaching for the edge of what can be known. It is the story of tools built to capture whispers in the dark, of theories forged to stretch imagination across the void. It is the story of patience, for the answers lie not in sudden revelations but in decades of vigilance. At the center of our galaxy lies a shadow. Around that shadow lies light bent into impossible arcs, and around that light lies the circle of instruments, machines, and minds devoted to understanding what it means. Together they remind us that science is not the conquest of mystery, but its constant pursuit. Sagittarius A does not yield its secrets easily. But with each orbit, each flare, each new tool, the boundary between ignorance and understanding is pushed outward, even if only by a fraction. And in that fraction lies the essence of discovery. At the center of the Milky Way lies a silence that binds us all. For every star that shines in the night sky, for every world that orbits in distant darkness, there is a common anchor, a hidden abyss, 4 million times the mass of the sun. We do not feel it in our daily lives. We do not see it when we look up at the constellations. Yet every orbit of every star, including the sun itself, is shaped by its pull. Humanity has always lived under its gravity, unknowingly circling a cosmic predator. This truth carries with it a profound paradox. Sagittarius A is both central and unseen, both essential and destructive. Its presence defines the Milky Way, yet it hides in silence. It is the heart of our galaxy, but a heart of darkness, beating without rhythm, consuming without sound. To reflect on this is to confront a deeper question. What does it mean to exist in a universe built not only on light, but on shadow? The galaxy can be imagined as a living organism, a great spiral body of stars and dust, stretching 100,000 light-years across. Its arms wind like veins, its clusters like cells, its stars like blood carrying energy across its structure. At the very core lies the black hole, its beating heart. It pumps not with light but with gravity, holding the spiral together, setting the rhythm of stellar motion. Without it, the Milky Way as we know it might not exist. Yet its nourishment comes through destruction. Stars too close are torn apart. Clouds of gas are devoured. Its heartbeat is both creation and annihilation. To live within such a system is to live with impermanence written into the fabric of reality. For black holes are reminders that even the brightest stars can collapse. That time itself is fragile, stretched and twisted until it ends. They are the universe's way of telling us that nothing is eternal. Not galaxies, not stars, not even the laws we trust to explain them. And yet, in this impermanence, there is wonder. Every atom in the human body was forged in the hearts of stars. Calcium in the bones, iron in the blood, oxygen in the lungs. Many of those stars lived short, violent lives, collapsing into black holes when their fuel ran out. In this way, destruction gave rise to creation. Death of stars became the seed of life. The black hole, far from being only an end, is woven into the chain of becoming that stretches from the first galaxies to the breath of every living thing on Earth. To stand on a planet, orbiting a modest star, within a spiral arm of the Milky Way, is to exist in relationship to the abyss. We orbit not only the sun, but the galactic center itself, carried on a journey that takes 230 million years to complete a single revolution. In the deep past, when the Earth's continents were fused into Pangaea, the solar system was in another part of its orbit around Sagittarius A. Dinosaurs rose and fell without ever completing a full circuit. Humanity in its entire history has not yet traveled even a fraction of the way around. We live as passengers on a voyage defined by the black hole's pull, though we will never feel its sway directly. This perspective reshapes the scale of existence. Human lifetimes are brief sparks against the slow rotation of the galaxy. Civilizations rise and fall in the time it takes a star like S2 to complete a single loop around the abyss. And yet in that brevity, we carry the ability to understand, to ask questions of the void itself. Perhaps that is the greatest wonder of all, that fragile beings living on a fragile planet can look across thousands of light years and recognize the heart of their galaxy for what it is. Sagittarius A also forces reflection on fear. It is natural to imagine the black hole as a monster, a cosmic predator waiting to consume, and in some sense it is. Nothing can escape its horizon. Nothing survives its pull once it crosses the threshold. But fear alone does not capture its essence. The same gravity that devours also shapes. The same silence that conceals also stabilizes. Without it, the Milky Way might be formless, scattered, unanchored. In this way, the black hole is not only a destroyer but a creator. This duality mirrors the human condition. Life and death are not separate. They are entwined. Every breath taken is borrowed from stars that burned out billions of years ago. Every life is sustained by impermanence, for without the cycle of creation and destruction, there would be no atoms, no planets, no beings to reflect on their place in the cosmos. The black hole becomes not just a physical object, but a metaphor for mortality, a reminder that endings are inseparable from beginnings, and so the paradox deepens. Sagittarius A terrifies and inspires in equal measure. It embodies the unknown, a place where our laws of physics collapse. It confronts us with our limitations, reminding us that there are questions we may never answer. Yet it also offers a mirror, reflecting back our determination to look, to listen, to imagine. The very act of capturing its shadow with the Event Horizon telescope was not merely a technical feat. It was a statement that humanity is willing to stare into the abyss and bring light from its darkness. The reflection reaches beyond science into philosophy. What does it mean to live in a universe where such objects exist? Perhaps it means that the cosmos is not designed for comfort, but for mystery. Perhaps it means that knowledge itself is a fleeting light, illuminating the vastness only briefly before fading. Or perhaps it means that in the very act of confronting darkness, meaning is created. For the Milky Way continues to turn, slowly, majestically, carrying us with it. Its spiral arms wind through time. Its stars ignite, burn, and fade. And at the center, Sagittarius A waits silent and patient. It will outlive every star now shining. It will remain when the galaxy's spiral arms begin to blur, when the Milky Way merges with Andromeda, when the night sky reshapes into unfamiliar forms. For billions of years to come, it will endure as the anchor of whatever future the galaxy becomes. Against such scales, humanity is small. Yet smallness does not mean insignificance. To be aware of the black hole, to know it is there, to capture its shadow, to ask questions of its mystery, this is a triumph of consciousness. It is the universe, through humanity, becoming aware of itself. Sagittarius A is not only the heart of the galaxy, It is also a symbol of our place in it. We orbit a monster and yet we survive. We live in a cosmos where annihilation and creation are inseparable, where every star owes its existence to cycles of death, and where every living being carries within them the remnants of ancient fire. To know this is to live with both awe and humility. And so the story closes not with answers, but with reflection. The black hole at the center of the Milky Way is a reminder of mortality, of impermanence, of the unknown. It teaches that fear and wonder are not opposites, but companions. That destruction and creation are not rivals, but partners. That even in silence there can be meaning. The galaxy turns, the heart beats, and in its shadow humanity dreams.